So good afternoon, everyone, and welcome to the last session of the meeting. And we have one talk in this session with Manish Jain from IISc Bangalore, who would be talking about flat bands and twisted bilayer transition metal dichalcogenides.
First of all, I'd like to thank the organizers for giving me the opportunity to present our recent work. This is the last talk, so the conference is over. So I tried to negotiate with him that perhaps I have no upper bound, but it didn't fly so well. So okay, so I'll try to tell you about some of the things that we've been recently interested in. So we've heard a lot of talks about flat band graphene, and actually Abhay Pashupati had talked about flat bands in TMDCs as well, which is transition metal dichalcogenides are often called TMDCs. So what I'd like to do is discuss some of our, just work through how we got interested in this and what our recent findings are in this area. As you all know, there has been a recent interest in magic angles in twisted bilayer graphene, and we heard several talks here about that topic. And the primary reason why people are interested in this is because, well, the reason people are interested is because it shows lots of interesting physics. But the primary driver of that interesting physics is that there are flat bands which are spatially localized at some stacking site in this twisted bilayer structure. And it shows a lot of this. This is a picture that you have probably seen more times than several times in the conference. So the question that we wanted to ask was, do you see similar flat bands in other 2D systems or not? And if so, is the origin of such flat bands the same as what the origin of flat bands in graphene is? So what I would like to tell you is that twisted bilayer transition metal dichalcogenides, which is a family of materials, molybdenum disulfide, tungsten disulfide, molybdenum diselenide, and so on. There are several members of that family. They also show similar flat bands. Okay, so this is not unique to graphene. This is something that Abhay had actually already mentioned in his talk. But what we'd also like to ask is, what is the origin of these flat bands in these twisted bilayer TMDs? Okay. So we're going to, we do a lot of computation. So what we're going to do is, we're going to construct a small angle twist between two layers of the bilayer of MOS2, molybdenum disulfide. This is one of the members of that family, which of course, as you all know by now very well, that it forms a moire pattern. Now, unlike in graphene, where if you twist by an angle close to 0 degrees, so let's say if you have two layers, you can make an angle close to 0 degrees, or if you can make an angle close to 60 degrees, which are the same. In these systems, because the sublattice symmetry is broken, you actually get different structures if you are angle close to 0 or angle close to 60. Okay, and this actually has some consequences. So in case you are interested in looking at these and playing around with these, we actually have a simple code which can actually generate these structures for you. Which can you can give an angle, you can give the lattice vectors, give the angle, and it will basically generate what the moire supercell of the structure is going to look like. Okay, so we do a lot of DFT computations. So all of the work that I'm going to present is actually going to be studied using density functional theory. So the problem, as you are probably aware, is that if you look at the large twist angles, then the number of atoms in the moire supercell is reasonable, right? Something that you can do easily with DFT. But as the angle becomes smaller, so let's say if you look at a 1.5 degree angle, this has 8,322 atoms in the moire supercell. And so that is actually a very, very difficult computation to do within DFT. And as I will tell you in a few minutes, it is very important that you actually relax your structure properly. Otherwise, you will actually get completely wrong physics. Okay? So as a result, doing this in DFT is a bit of a challenge. So what we ended up doing because you can't really do DFT and relax the structure on a computer. This will take forever. so what we ended up doing is we actually, because if you think about these two layers, and if you think about how they are talking to each other, they're just talking to each other with van der Waals interaction, right? I mean, structurally that is all that's how they're talking to each other. So essentially, for structural purposes, you can actually write an effective force field, which will help you in relaxing, because you're not breaking any bonds, you're not doing anything, you're just moving stuff around a little bit when you relax the structure. So you can actually write an effective force field, and this was actually something that people had worked out how to do that for the case of graphene. So if you did something which is something like a standard Lennard-Jones, it would not work very well, because the AA site and the AB site have to have different energies, and this will not, Lennard-Jones will not capture it. So you have to do something a little bit more sophisticated, but it's well known how to do that. So we actually worked out a force field which allows us to do that. And with that, then you can, once you have a force field, then you can actually study a whole bunch of structural things once you know how to relax the structure. And then we actually take the structure from these force fields and then do one shot DFT to actually get the band structure and see what we can learn from there. Okay. So this is something that you have probably seen before. In graphene, there are these two kinds of high symmetry stackings. One is called the AA stacking and the other is called the AB stacking. In TMDs, there are actually 5 of them. So there's another one which is called the Bernal molybdenum on sulfur stacking, and it looks like this, and then there are 2 more. Okay? So when you construct a twisted structure, you will get some or several of these stackings present in one of your twisted structure. Okay? So for example, let's look at at 2 layers which are twisted with respect to each other by an angle of 3.5 degrees. Okay? So in that case, you will see that there are 3 stackings which are possible. Of course, these 2 are the same. Bernal sulfur on moly is the same as Bernal moly on sulfur. But essentially, if you look at this, if you look at the structure, you will find that if I put the AA stacking at the place where I rotate, then I will essentially get these 2, and then it will come back to the same one, and that is my Moiré cell. Okay? So the interesting thing about this is, of course, all of these stackings have different energies. The structurally, different stackings have different energies associated with them. This is just a structural energy per formula unit. And if you, for example, go along this body diagonal, you will find that the energy varies in some strange way. So you can ask the question, what does this energy, I mean, of course, the system has these high energy stackings, which are actually topologically have to be there. You cannot get rid of them. So the question is, what can the system do to actually minimize its energy in such a case? And I will get to that in a minute. Near 60 degrees, which is unlike in graphene, you actually have 3 distinct stackings, which are not the ones that you got near 0 degrees. You have the AB stacking, which is your regular bilayer, which is the most stable stacking. You have the Bernal moly on moly and Bernal sulfur on sulfur. Okay? And here, unlike in the other case, the 3 stackings, in the previous case, if you remember, the Bernal moly on sulfur and the Bernal sulfur on moly actually had the same energies. Here, if you go along the body diagonal of this Moiré, if you go along this diagonal of the Moiré supercell, the 2 stackings are distinct and they actually have different energies. Okay? So when I do a relaxation, some effect of this will actually show up in the relaxation pattern. Okay, so once we know, once we have, this is near 56.5, this is slightly less than 60, so 60 minus 3.5. Okay? So what we noticed is when we started relaxing the system, this is a busy slide, but essentially all I want to point out is that, so the simple picture that you have, that if I take 2 layers and I rotate one with respect to the other, that the sheets remain flat is not true. Right? When I rotate 2 layers with respect to the other, and I let the system relax, because the stackings are different, and different stackings have different equilibrium spacings, the sheets bend. Question is by how much? And actually, you can see the scale on this side is the separation between the moly to moly distance. It can vary, it's quite a lot. It's half an angstrom or more. Right? So these sheets are actually not flat. These sheets are bent. Why does it matter? Because obviously, if you think in terms of a tight binding picture, then your hopping will change. It depends really. The interlayer hopping really depends on how these are bent and so on, the details of how these are bent and so on, because it depends on the distance. So depending on if the lower energy structures have a different interlayer separation and so on. So basically, the sheets are no longer flat. That is the main message that I want to first tell you. Yeah.
Still preserve this Moiré unit.
It does preserve. In this case, it does preserve the Moiré unit cell. Yeah. There are cases when it doesn't, and that was a poster outside that Indrajit had presented. But in most of these cases, it preserves the Moire. Okay. So then what you can do is you can say, okay, fine. You're doing a DFT, you let the thing relax. This is maybe 1500 atoms, they're about the limit of what we can relax in DFT. And you ask, how did the atoms really move? The atoms actually move. So how do I construct it? I construct it by a rigid rotation, and then I let all the atoms move and see where they finally end up. So what you find is, what you expected, at least what we thought initially was, okay, it'll move out of plane. I mean, after all, that should be fairly soft to move. But really, it should not move in plane, because that will cause strains within each layer. But turns out it actually does move in plane. So in plane, you will see that the atoms are moving in some strange way. I mean, one is moving clockwise, the bottom layer is moving anti-clockwise. So the atoms are actually trying to do something. And really what they're trying to do is what we'd like to understand. So basically, the atoms are moving in some strange way so that something is happening. Obviously, the energy is getting minimized. But really, how is the system trying to minimize the energy is what we'd like to understand. And in order to do that, we actually define an order parameter. So this is a structural order parameter. So the structural order parameter is, so if I take, because I have to define two order parameters. Now I have to define one order parameter for stacking near 0 degrees and one order parameter for stacking near 60. Why? Because a simple translation cannot take me from one to the other. Okay? So I'll define the order parameter as the shortest vector that will take me from any stacking to the highest energy stacking in that particular Moire pattern. So I had two highest energy stackings in every Moire. I had one highest energy stacking in every Moire pattern. I'll define for every whatever stacking that I have locally. I will say, okay, the order parameter at this site is essentially what will take me to the highest stacking at highest energy stacking. So how much do I need to translate the cell by, so that actually I recover the highest energy stacking. Okay, so there's one order parameter near 0 and one order parameter near 60 degrees. So for example, if you look at let's say the high symmetry stackings, and you said, okay, what does the order parameter actually look like over here? So for example, this is the highest energy stacking. So by definition, the order parameter is 0 here and is 0 here, because this is the highest energy stacking in this particular Moire near 60 degrees. So if I look, for example, if I look at the angles near 0, then for this particular Bernal M1S, I have three possible choices of how the system can move and actually get to the AA stacking. Okay, so this is these are my possible directions, and the length of this vector is 1.8 angstroms. Okay, so I can translate this unit cell. So if I have one unit cell, I can translate. If I give you Bernal molybdenum on sulfur stacking, I can translate it by 1.8 angstroms and actually recover my AA stacking. And similarly for the other one, there is some other directions in which I have to move, and the magnitude is again 1.8, which is half the cell size, actually half the unit cell size. Okay. So now what I'd like to see is, once I've done the relaxation, what exactly is happening inside the system. So once, so I plot. So this is if I just rigidly rotate the two sheets and I form the structure, this is what the magnitude of the order parameter looks like. So near 0, it looks like this, and near 60, it looks like this. The scale here is I should have put the scale. The light is I think 1.8, and this dark is the dark is 0, right? So because that's the stackings that I have. Okay. So now if I relax the system, what I find is that the order parameter is changing everywhere. Okay. So clearly these places which are the high energy, which are the AA stacking in this structure, cannot be removed. I mean, this is topological, right? So at some level, once I make the structure, I can't get rid of them, right? But what the system is really doing is, it is actually inducing local strains in each of the layers, such that it actually gains in the stacking energy. So there's a trade-off between induced strain and actually the stacking, gaining some energy from the stacking, and that's essentially what the system is doing. Interestingly, if you look at this, you can see that the angles near 0, they have a 6-fold symmetry around this stacking, whereas over here, it only has a 3-fold symmetry, right? And that is primarily because if you think about the fact that you had two minima in this angles near 60, which were inequivalent, they don't grow by the same amount. Whereas over here, both of these minima grew by the same amount. Here, they don't grow by the same amount, and as a result, you actually don't have a 6-fold symmetry here. Okay. So this is the magnitude of the order parameter that I had plotted. But if you look at the actually direction of the order parameter, you will find that the order parameter is actually changing direction along these lines. So in between these lines. So these lines separate along on one side of this domain. The order parameter points in one direction, and along the other, it points along the other direction. And if you actually plot, okay, so that is the case. I will get to the change in the order parameter in a second. But also you will notice that if you look at the interlayer separation, you can actually define the separation between the two layers locally and ask how does the interlayer separation landscape look like. It looks something like this. So again, you see the 6-fold symmetry here, and it's not 6-fold symmetric over here. If you start looking at the strains in each of the layer, you can ask, how does the bond length change in each of the layers? You find that the bonds, that the region is actually that some of the regions are actually strain free, and the strain is confined to some regions around these lines that I had drawn previously. And so the question is, what is actually happening at these lines? And if you look at these lines, basically you look at the order parameter on one side points in the other direction, and the order parameter along the other side points in the other direction. If you take the difference, it actually points along the line, the direction of the line, and these are actually nothing but what are known as strain solitons. Okay, and if you do, for example, they're solitons because if you do a finite temperature calculation, you will find that these things will move together. They're always linked to the same dots. They don't, none of this topology will actually change when you try to do this. Okay. So so this is about the structure. The question that we really want to ask is, fine, you relax it, something happens. Okay, how does it affect the electronic structure? That's really the question that we would like to ask. So let's look at the angle near 2.6 degrees, and again, this is the k and the k prime, as you would, sorry, k and k of one layer and k of the other layer, and the Moiré-Brillouin zone is much smaller. And so if you have to look at the electronic structure, it's important that, because your Moiré cell is much larger than your original cell, there'll always be band folding. When you plot this electronic structure, of course, this, you'll plot it along some directions, gamma to m to k to gamma, in the Moiré-Brillouin zone, right? But most of it is just band folded, right? So if I take just a pristine AB stacking and I band fold it, if I look at the bands, they'll look much flatter, but actually they're not flatter because I've not done anything. I've just taken the same structure and plotted it in a much bigger cell, so it's just band folded in. And as a result, I will just find that if I calculate, for example, the effective mass or everything, it will exactly be the same. But I will not find any gaps in the system because it's just band folded stuff. But now if I actually look at the Moiré cell, the relaxed Moiré cell, and I look at what does the band structure here look like, I start to notice some interesting features. So there are gaps opening up in this thing, which is okay. But I start looking at this bands, and they look sort of look flatter, right? Because the dispersion here was more and there were no gaps, and now I have gaps. So of course there will be gaps in places, and as a result, if you calculate the effective masses actually do become higher. Okay. So it's not just that it's band folded in, it's band folded in and it has a slightly different effective mass. But also if you notice here, if you just look at this one, and you forget what the scale is, this is just the valence band maximum, near the valence band maximum where I've blown up all these bands. If you just look at this actually looks a lot like the graphene band structure, at least the two band, PZ, if I just took two in a unit cell, if I look at that, this exactly looks like that. So we'll see why it looks like that as well. Second. So I can take these bands, and I've blown up the region in near the conduction band minimum and the valence band maximum, and I actually just plotted what do the bands actually look like. And you see that the valence band bands actually look something like this. Now, if you didn't know the scale here, and you forget the scale, and you just imagine these to be two sites in the graphene lattice, actually this is just like the first two bands are basically forming the graphene-like graphene-like dispersion, which is the reason why you actually see a graphene-like dispersion over here and a crossing at K. So obviously, unless you put some strain on it or do something else, you're not going to be able to open a gap here, in the same reason as you would not be able to open a gap in the graphene, right? But on the other hand, you see that the conduction bands are completely delocalized, right? They're just everywhere. So the question then is, okay, so fine, so you have this, so where are the flat bands then? So of course, you can argue that these bands are not, they're band folded, so they're separated from the rest, so perhaps these will become like a flat band. Let's see for a second, let's see what actually happens. So first the question is, why do the bands localize? But you also notice that there's no wave function at the AA side, but over here of course they're both equivalent, so it should be there. But the valence band wave functions seem to avoiding the AA sites, and so you can ask, why does it avoid the AA site? So the explanation for that is fairly simple. You can look at the ideal unit cell band structures for all these high symmetry stackings, and you look at their equilibrium interlayer spacing, because essentially what happens is when you let the system relax, these stackings come to their equilibrium spacings, and you ask which are the states which are at the top. If I line them up with the vacuum, I can see which are the states which will fold in, right? Because that is the ones that will get folded into my, So clearly from here, I can see that the AA valence band is much below the Bernal M1S valence band maximum. So when I fold bands in, I expect the wave function to be at the Bernal M1S, because that's where the bands will fold in. There is no wave function at the AA site at this point. That's one simple way of analyzing and figuring out where the bands will be localized. Another way of looking, but on the other hand, you see that the conduction bands all line up. If the conduction bands line up, I don't expect any of such argument to hold for the conduction bands, and so I should not see any localization along the conduction band in the conduction band, but I should see some localization in the valence bands by a la this argument. Another way to look at this is to ask the following question. So, in graphene, when we talk about the localization, we talk about there's a hopping between the layers, and that causes the bands to be where they are, and the flat bands to occur where they are. So we can actually start looking at a hopping in a slightly more different way, which is the following. We can say, look, if I take two sheets of MOS2 and I put them very far apart in a unit cell AB stack, to put them very far apart, they don't talk to each other, right? So if I look at the planar average potential, then this is what the planar average potential looks like. And so this is where my sheets are. I put the sheets like this, right? This is what the density is, right? And the potential is over here. But if I look at the potential over here, then I can track what happens to this potential as I bring the two layers closer. And as I bring the two layers closer, there should be some tunneling between the two layers. And as a result, the barrier between these two layers, if you wish, will come down. Right? And I can track that barrier to actually use as a surrogate for some hybridization between the layers. Right? So as I'm showing you, if I bring the layers closer from the previous one, I brought them slightly closer. The barrier is no longer at that point, and if I bring them to the equilibrium spacing, I find that the barrier is reduced. So what I will do is I will track this value of the maximum potential between the two layers as some measure which is telling me how well these two layers are hybridizing. Okay? And I'll try to, and so that is one way in which I can measure the hybridization between the layers. But the other thing that I notice is that, there are various stackings inside this. So I can also ask the question, is there any in-plane potential that has developed? Right? So, this is inhomogeneous. Everything is inhomogeneous. I talked about a hybridization which is between the two layers. But in the plane, because I said there are strains, is there any potential that develops within the plane because of this relaxation and so on? So I can define a confining potential in the following way. I can take the Moiré, I have the potential for the entire system. I can basically average it in the out of plane direction, right, and average it in a unit cell, and now I have a number for every unit cell, and I can track how this number is changing inside the cell, and I'll subtract the AB just so that I have a number which is reasonable around 0, and then I'll be able to see how this looks like. This is what I'll call a confining potential. This is in plane, the other one was out of plane, right? The reason why I'm doing this is I want to understand where does the flat band, or where does all of this arise from. So if I look at the in-plane if I look at the confining potential for angles close to 0, basically find nothing. There are no features here. There's nothing there, right? So essentially there is no in-plane potential which has developed which is causing any confinement. On the other hand, I find that the hybridization, this barrier that I was tracking, is highest at these points and lowest at these points. So now I can easily argue that, look, if the barrier is the lowest, that means the hybridization is the largest, and therefore that is the regions where my wave function should really be localized, because really that opening of the gap basically determines what becomes the valence band, and therefore if the hybridization is largest here, this is the places in real space where I will have the wave function localized. So this is fine, and it actually explains what happens near 0. You can also look at what happens as a function of angle, and as you can imagine, if you look at just the valence band maximum, you can see that as you change the angle, you decrease the angle, all that is happening is that this bandwidth is becoming smaller and smaller. So in that sense, it is like graphene, and you are basically have these two orbitals which were centered at the Bernal M1s. They're becoming further and further apart, and as they become further and further apart, it's basically, there's less hopping, and essentially this is just a scaled version of graphene. So basically, what this also means is that there's perhaps no magic angle per se for angles close to 0. Because all that is happening is this graphene band structure becoming thinner and thinner and thinner, and that's all that is happening. Nothing much is happening beyond that. Okay, so now near 58 degrees, something completely different happens, and this is actually the more interesting part. So near 58 degrees, as you know, K and K prime are closer together because it's near 60 degrees. When we do the band structure, this is at 58 degrees, you find a band structure that looks like this. This is, to put it politely, is nuts, right? Because where is my original MOS2 band structure here? So then, of course, what you do is you start looking at the wave function and seeing whether you can make any sense of what does this band structure correspond to. You notice that these are flat bands. I mean, these are flat up to, as far as we can tell, right? You plot the first wave function and it looks like this, and plot the second one, it looks like this. Third one, it looks like this. This is a valence side wave function that we are plotting. And then you start realizing after a while that these are actually nothing but these wave functions. Each of these looks like the solutions of an infinite equilateral triangular quantum well. Okay. So essentially, somehow the system is developing some quantum wells which are triangular in shape, and I just have a real space localization of states inside that. That is all that is happening. Okay. The conduction band also shows something similar, but the localization is, if you notice that the valence bands are localized here, the conduction bands are localized over here. So they're spatially separated electrons and holes, if you wish, in this. So you ask yourself, where is this confining potential coming from? So of course, if you plot the inhomogeneous hybridization in this picture, you will find that the hybridization is still inhomogeneous and the barrier is high over here. So nothing should localize over here. But on the other hand, the barrier is lower over here and here, so things can localize at both of these spots. But when you start plotting the confining potential, which is the in-plane potential, right, you start noticing these triangular patterns. And if you look at the scale of this thing, it's about half a volt. So basically, I have an array of half a volt equilateral triangular quantum wells, equilateral triangle quantum wells, which is where my electrons and holes are getting localized. So clearly, my electrons should go inside the well, and because I have a negative potential between the two, my holes should localize over here. So that's actually what happens. The electrons go here. They should never go, nothing should go at the red spot. The holes go over here. That's exactly what happens. So now you can ask, where does this triangular, we had relaxation in both of these things. Why does this happen over here? So one thing is, you can say this is because of the relaxation. That's easy, but can you show that this is because of the relaxation? The simple thing to do is remove the relaxations, right, and see what happens. If you remove the relaxations near 60 degrees, you don't find any of the states that you expect. So clearly, this is coming from such relaxations. Then, of course, you can go and you can plot the density of states for a whole bunch of angles near 60 degrees as well. And you notice that because near 0, it was only coming from hybridization, nothing really comes in the gap. Whereas near 60 degrees, you find because there's a quantum well which will localize my electrons, and that is actually below. So basically, my valence edge is determined by the well in the holes, which is like this, and the electronic one is determined by the well in the electrons. And so effectively, my gap has reduced over here, and it's essentially all the states are coming from. The electronic states are coming from an electron well, and the hole states are coming from a hole well. So to conclude, what we have shown is that there are no magic angles in small angle twisted bilayer MOS2, and we expect a similar kind of things to happen in other TMD layers. So why we say there are no matching angles? Of course, there's a whole range of angles where the bands are absolutely flat. So there's no one angle to hit, right? Near 0 degrees, the valence band, it was just it was just dependent on your bandwidth was dependent on how large your Moiré lattice was. So it didn't really matter very much. We also show the formation of triangular quantum dots, and these triangular near 60 degrees, and these dots actually separate the electrons and the holes. So this should have some interesting optical properties. Yeah. The other thing about this system then is that you have to keep the relaxations in mind, and without relaxations you actually don't get a lot of this stuff, which will, if you don't keep this relaxation in mind, you'll actually get something completely wrong. Now I should thank the people who actually did the work. Most of this work was done by Meet, who is now at Berkeley, and Indrajit and Sudipta, who are also in the audience, also contributed to the second half. Thank you all.
Thank you, Manish. Questions?
Why you preferred ISTA over other pseudo-potential codes?
Oh, because 8,000 atoms. Very hard to do anything else. We benchmarked.
ISTA doesn't give good results for relaxation.
We didn't do relaxations in Siesta. So the relaxations were all done in a force field. The force field was parameterized with something, with something that we made sure. So the force field was parameterized with some DFT results done with quantum espresso. Once we had the force field parameterized, we relaxed the system in the force field and did a one shot with Siesta. With 8,000 atoms, quantum espresso will, it'd still be running the calculation.
So the idea of doing this whole near 0 degree and near 60 degree was that to understand that what is the origin of these set of flat bands. So like the flat bands you showed us is this triangular potential whale.
That's right.
Story.
Yeah.
And you also showed us that without the relaxation, they actually disappear, right?
Well, so in that picture, what we had done is we had allowed for the out of plane relaxations, but no in plane relaxations. You can say don't allow any relaxations. You see flat bands and say, okay, fine, then I'm okay, except they're localized completely at the wrong spot. Here we showed where the electrons should localize and where the holes should localize. That's not where they localize if you don't do any relaxation. Because the physics is that you have to form this confining potential. If you don't form the confining potential, you may get some other localization, but that is not what the system will actually do.
I have a second part in that regard. So this is this Balin formulation where you can write down these stories, these relaxation problems in some internal gauge theories, right?
Okay.
And so is there anything one can do in these problems? Because it seems like the pictures that you've shown, it looks like there is a current going, there's a flux like behavior.
No, so that picture was, so that's actually a little misleading. I mean, when I first saw it, I thought that there's something going around. But really that picture is initial and final position and a vector connecting the two. So there is no, I mean, there's no current flowing in this direction, even though I showed arrows. So there's no current flowing in that direction. The order parameter actually is going around, by the way. So if I plot the order parameter, then there is a place where the order parameter actually goes around some of these topological deep.
But I understand. But I'm asking that the picture that shows,
can
we think of that as a strain gauge potential?
You can you can write a continuum model for this. In fact, I think Kaxiras, Professor Efthymios Kaxiras from Harvard has actually written a model for a continuum version of this. And you can capture some of these effects there. Yeah. So you can write a continuum model for this. Yeah.
Thank you.
More questions?
Bands.
Yeah.
Is that tunable?
That's dependent on the size of the quantum well.
Is that tunable?
Yeah, you change the angle, this thing changes. So if you look at, for example, some of the density of states, you can actually see. So if you look at the density of states, you can see that depending on what angle I'm at, the states are. It's basically just particle in a triangular quantum well, right? So that's essentially all. Okay, so energetically stable meaning, I mean, so we have calculated phonon spectra for these. So what we find is that at angles close to 0, the phonon spectra, there are no negative frequencies, barring some bending mode related things, which you can double the cell and get rid of. Near 60 degrees, an angle which is much smaller than 1.5, actually 1.5 seems to be the threshold, below which actually there's a lattice reconstruction. Lattice reconstruction at the Moiré length scale. I think Indrajit has a poster about this, had a poster about this outside. But once you do the reconstruction, you can find a structure which is stable.
More thing, if you have different twist angles, the strain is different for, I mean, the atoms bonds are.
The bonds are strained. The order of strain is about 1 to 3 degrees. Basically, the strain is localized on these strain solitons. So what happens is the system says, I'm going to eliminate all the strain from the stable stackings and actually push the strain towards these solitons, and that's where the order parameter quickly changes, and that's where the strain is localized.
So since that means the states are quite localized around the flat band region. That
the
means
strain
that,
is localized on the
yeah,
solitons.
so because of that, because of the flat band, the states can be localized. The density of states can be localized of the atoms around the flat band region.
No, the density of state, the flat band is coming from the triangular potential, right? The strain is localized on the solitons. Is that what you're saying? Or?
No, I want to ask another one is, around the flat band, the states are quite localized. The
flat band is localized states, yes.
If that is the case, can we expect a stable spin polarized state?
Okay, so that's so you are asking, if I put spin polarization, how does the picture change? Yeah. If it does. So so this is all done, we have not doped the system. This is all done undoped. So I think once you have to do for that you have to do something more sophisticated than what we've done. Essentially you have to take this and maybe you'll form the stuff that other speakers, for example, the stuff that Ashwin was talking about, maybe you'll form Mott insulators at half filling and so on, which I don't know. We've tried putting spin orbit coupling in, because this valence band hybridization, how does it change? It turns out near 0 degrees, near the gamma point, spin orbit coupling is anyway 0 in these systems. So it doesn't really make a difference. But both of the bands are, this flat band, both of them are occupied in our calculation. It's an insulator, so both both up and down are occupied, so it's just, there's nothing happening there.
Manish, I can ask you later, but I might forget. So one of the key properties of chalcogenides is a very strong light matter interaction, because the interaction length between is very short or rather the cross section is very large. Do you expect the same to happen in this?
So so the thing is, you have formed a patterned structure now, if you wish, right? You have these triangular quantum wells. So your electrons and holes are in real space separated. So I don't know. I mean, the cross section to excite them may be lower, as well as the cross section. Maybe the lifetimes will be higher. I don't really know, because the decay. The electrons and holes are now separated, right? So I don't know how they will, they will have to recombine in a strange way to give you something. So I don't really know. So we were thinking about doing 2 particle, but this is too large a number of atoms.
Further short question.
It's a very short question. So, so as you mentioned that this problem, the particle hole symmetry is broken. The sublattice symmetry is broken.
That's right.
AB sublattice symmetry is broken.
Yeah.
But we have seen before in Ashwin's formulation that the flat band is connected to the sublattice symmetry point and perturbatively connected.
So that is, so I don't know. So they had also talked about chirality in the system. I don't, we don't know whether these are coming from a different reason. So I don't know whether these are chiral or not. So all of those things are something that we actually don't know.
Thank you. Thank you very much.
Okay, so with that, let's thank Manish once more for the nice talk.